Alright, we're going to look at the mean value theorem today and then talk about monotonicity, which is just a fancy word for talking about where functions are increasing or decreasing, basically. And I think we kind of already know the basics of how this is going to work as far as the increasing or decreasing part, but I wanted to talk about the mean value theorem first. And it's a more general theory or theorem than the last theorem we looked at in the previous lecture video set, which was, we talked about Rawls' theorem. Rawls' theorem is a special case of the mean value theorem. So here it is, the mean value theorem. Assume that the function is continuous on a closed interval from a to b and differentiable on the open interval from a to b. So remember the connection there. If a function is continuous, it is not necessarily differentiable, right? Continuous functions can have sharp turning points, cusps, right, where the derivative does not exist, or you can have vertical tangent lines, and so we're kind of making it smooth and continuous, right, in a sense, so by the differentiable portion there. So if that's the case, then we know there exists at least one value c in the interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. Mean value theorem is essentially an existence theorem. It's saying there's at least one of these numbers in the interval from a to b where the derivative, right, of the function is equal to this. And what does this thing here represent? Well, it really represents the average rate of change of the function over that interval. So let's take a little look at this graphically. So we're going to talk about the interval from a to b. And let's sketch a possible function here. Let me just say this is my function f, which is continuous, right, smooth or differentiable, as indicated here, right? There's no holes, gaps, jumps, breaks, discontinuities of any kind, and also it's differentiable everywhere. It's smooth and continuous, no vertical tangent lines, etc., etc. All right, so first off, I want to talk about, well, if I come up vertically and hit that point there, right, and come up vertically and hit that point there, I can draw a line connecting these 2 points. If you remember, that's called a secant line. And the question is, what is the slope of this line? What is the slope of this line? Well, this point here, right, is the point what, a comma, that point right there is the point a comma f of a, right, input comma output. And this point here is the point b comma f of b. So you think about the slope of this line, right? It's the vertical change, right, as I move from this point to this point. And the vertical change is the difference of the y-coordinates, so f of b minus f of a. Notice that's the numerator here, divided by what the horizontal change, right, going from this point to this point, which is just what the difference of the x-coordinates, b minus a. Right? So that is exactly what we're saying. The slope of this line is the average rate of change of the function f over the interval from a to b. And so the mean value theorem is saying there's some value c in this interval. C is an input, right, an independent variable here. Some value, at least one value of c, such that what the derivative of this function is equal to this average value, is equal to the slope of this line, right? It's equal to the slope of this line. And remember what the derivative is? Well, it's the slope of the tangent line, which is, sort of the instantaneous rate of change of the function at that point. So I'm going to show you where the value c occurs. So look at the top of my ruler. It coincides right now with that line I've drawn. And what I'm going to do is I'm going to move the ruler up, keeping that same slope. So think about, drawing a line now at the top of the ruler. That line would have the same slope as the line I drew. Therefore, they're parallel, right? Looking at parallel lines. And I keep moving this up until what? I want to become tangent to the graph of f. And I become tangent right about there. Right? So now if I draw of this line here, that's the tangent line to the graph of the function f, where? Well, right about there, and let's drop that down. Right. There's one c that's guaranteed by the mean value theorem. This line is parallel to the line I drew, so the derivative of the function f at c is the slope of this red line, which equals the slope of this line here, right, which is our average rate of change of the function. Okay. Notice there's another value of c, because if I were to draw parallel lines to this one going down just a little bit, notice I hit the graph of the function. I'm tangent to it right about there, just a little bit. Probably didn't draw that the best. There we go. So right there, there's another c value. There's at least, we'll call this C1 and C2, right? They're different c values, but there's at least one c, and we've got two in this instance. And depending on how the function looks, we could have multiple places where this occurs, but we're guaranteed at least once. Okay. Now that's the mean value theorem. Now, as far as applying that to situations, it's not used a bunch. We certainly, in proving some other theorems, for instance, later on we'll use it to help us prove in Calculus 2 the fundamental theorem of calculus, which is a very important theorem. And it's very useful in proving other theorems. Here's a little analogy that might be helpful. If we think about the function here representing the distance from a fixed point undergoing linear motion, and the independent variable, the horizontal axis here, is time. So over time, how far you are in say miles or feet from a given point over a certain time. Then what do we have here? The average rate of change of the function from time A to time B is just the average speed, right? The rate of change of the position with respect to time is your average speed, or average velocity, I guess I should say. That's your average velocity, which is going to represent this. The derivative at any point, right, the slope of the tangent line will indicate what? The instantaneous rate of change, or the instantaneous velocity. And so what the mean value theorem is saying is, if you're traveling for a given time period, undergoing linear motion, then at some point in time your instantaneous velocity must be equal to your average velocity over that time interval. That's what that means, at least once. So for example, be careful if you're traveling along, say, a toll road, like it may be in Florida, where you get on the toll road and they give you the ticket showing the time you got on, and then you travel for a period of time and you get off and you hand them that ticket, that little stamp. They'll know exactly how long you have traveled. They will know how far you've traveled. They know where you got onto the toll road. They know where you got off. So they know your distance traveled. They know the time that you traveled at. Therefore, they know your average velocity. So let's suppose you traveled for 2 hours, and you traveled 180 miles. Right, 180 miles in 2 hours. What's your average speed there? 180 divided by 2 is 90. That means you're guaranteed to have traveled, at least one time, 90 miles per hour. And so be careful, because if the speed limit is 70, you could be in trouble, especially if the toll attendant has taken calculus before, right? Then they may give you a ticket. Okay. That's the mean value theorem. So what I want to look at now is, this theorem simply says that these values, or value of c, exist. It doesn't tell you what they are. How could you find that value? So let's take a look at a problem where we're going to do that. Let's find the value of c guaranteed by the mean value theorem for this function, which is a very familiar function, the square root of x, over the interval from a equal 1 to b. And so first let's look at the average rate of change of the function on the interval from a to b. Right. So f of b, what's f of b? b is 9. F of 9 is the square root of 9. F of a is the square root of 1 over b, which is 9, minus a, which is 1. Well, the square root of 9 is 3. Square root of 1 is 1. 3 minus 1 is 2. 9 minus 1 is 8. And I get 1/4. Okay, 0.25. All right. So we're guaranteed that the derivative of this function is equal to 1/4 for some value of x between 1 and 9. Right. Well, we're going to need to know what the derivative of this function is. So the function, right, is square root of x, or x to the 1/2, and so derivative is by the power rule, right, which is, we can write as what, 1 divided by 2 square root of x. Okay, and so mean value theorem then says that there is some value c such that the derivative is equal to what? The average value 1/4. So if I plug in c to my derivative, I get this equation here to solve for c. Well, can you figure out what the value of c is to make this equation true? Think about it. The numerators are the same. I need both denominators to be 4. 2 times what is 4? Well, 2. I need the square root of c to be 2. When's the square root of c equal to 2? 4, right? When c is 4. Right? Square root of 4 is 2. So there's my value of c guaranteed by the mean value theorem. And again, there's at least one. There may be, more than one depending on the particular function in the interval you're talking about. So I'll just show you this picture here. Here's the graph of the function, the square root of x, right here. And we were looking at from the interval from 1, right, when x is 1, output is 1, square root of 1, to b equal 9. 9, square root of 9 is 3, is that point. And so if I were to connect these two, let me do that here. There's the line, the slope of which is what? 1/4. That's the average rate of change of the function from the interval from 1 to 9. And just confirm that if I go from one point to another, notice I'm going up 1 and over 1, 2, 3, 4. Up 1, over 1, 2, 3, 4. So that's the slope, it looks like, of this line. And then if I sort of say, okay, well, I want to have the tangent line but have the same slope, so I just continue to move this line. Look at the top of my ruler. I'm going to keep it parallel to that blue line that I've drawn until I just barely touch the graph. Looks like somewhere right about there, right? There's my tangent line right there at where? It looks really close to what? 4, which is the value of c that we came up with.